Thank you, Dave, and thank you very much for inviting me. Oh, look at Danny. Look at that beautiful sun. I'm jealous. Oh, anyway, I'm going to tell you a little bit about SU2 representations of three manifolds that are of this form, meaning it's going to be a default cover over a knot, and I'm going to assume that this cover is an integer homology sphere. Right, and then before I forget, this is joint work with Shudipta Ghosh and Shenkun Lee. And so let me show you this chart that I made. Is that big enough, or should I make it bigger?
Make it bigger.
Yeah. Is this better?
Better.
How about this?
Perfect.
Okay, so here's the idea. So the question is, if I have a knot, and I have a degree for a cover, if the cover is and if the default cover is not an integer homology sphere, I'm going to ignore it. And then this is one of the main results that I'm going to use. The fact that when we have that the degree is 2, we already know that the cover, that the three manifold, that the integer homology sphere is in fact or admits an SU2 representation. So this is a combination of work of Kronhammer Morocco and Cornwell and Sivek. And so then, okay, so we started this project asking ourselves, what about the other degrees? And the first observation is that we have knots are going to be of three types. They're either going to be satellite knots, they're going to be torus knots, or they're going to be hyperbolic. If the knot is a torus knot, then the branch cover is a Seifert fiber homology sphere, and like in the 80s, Fintoshel and Stern solved the problem. So we already know, and so I should say it's not only solved, but the answer is yes. If the knot is a satellite knot, then their branch covers are going to be toroidal, meaning they admit a separating torus that is not compressible. And so work with Ty Liedman and Raphael Sender shows that in that case, they also admit representations. I should also say that there's a proof by Baldwin and Sivek of this same fact. So two different proofs. And so the last one is hyperbolic, right? And so this one is interesting for two reasons. One, because if I have a hyperbolic knot and I have the degree of the cover is 3 or higher, then a result of Thurston tells me that my three manifold is going to be a hyperbolic three manifold. And so in this question, let me go back. In this question of given y an integer homology sphere, does there exist, and this is the way, does there exist an irreducible representation? Or in other words, non-abelian. Right? So this question can be answered in a similar manner, right? If y is Seifert's fiber, if y is toroidal, right? These are the ones that I'm saying we're done. And so the only open case is if y is hyperbolic. So the actual motivation of this project was tackling this third case. Maybe in a subset of all of the hyperbolic integer homology spheres when we have extra structure. And so, but we have a little bit more information going back to just the general setting. If we know that the signature signature function at one of the d root of unities is non-zero, then a result of Colan already, maybe Chris Harold, I don't know who to attribute it to exactly, but it tells us, yes, we do actually have an integer homology sphere. And then there are other results. For example, if we have that the knot is quasi-positive and the four-ball genus is strictly positive, so if the knot is quasi-positive and not slice, then using work of Baldwin and Sivek on one hand and Harvey, Kawamura, Plamenskaya, then we also get the existence of SU2 representations. I should say that in this work of Baldwin and Sivek, and also this one, we get the existence of a representation by showing the non-triviality of some instanton knot groups or instanton homology groups. And then, so what I'm going to tell you today is how we can just assume that the knot is two periodic, or that knot is the closure as a special type of closure. And then in that case, we're going to get the existence of SU2 representations again. Okay, so let me then do the first part. So part one, two periodicity. So we say that a knot in the three sphere is two periodic if there exists a self-diffeomorphism of the three spheres such that it is an involution, it leaves K invariant. But if we look at the fixed point set of F, let me call it A, then we have that this intersection is empty. So A is for axis, because then what happens is that it ends up being that K, sort of like the trefoil. Here's my axis. And the knot is invariant under this involution that has, in this case, the involution is rotation with respect to that central axis. Okay, so this is an example of a two periodic knot, and in fact, all of the knots that are two periodic are going to be of this form. And so what the key here is that I can then take the quotient. So all of this is happening in S3, and I'm going to take the quotient of S3 by this involution. Well, it turns out this is again S3, and I get a two component link AQ and KQ. Okay, the quotient link. And so why do I know that two periodicity is then going to guarantee the existence of SU2 representations? Because it turns out that, so this is the lemma or theorem or proposition, I don't know how you want to call it, but if K is two periodic and D is such that this is, actually, I don't need this, but I'll ask a question in a minute to the audience. If I have that a knot is two periodic, and the linking number of between the two components of the quotient link, which is the same as the linking number between the two components of my original link, of my two periodic link, is relatively prime to D, then the d-fold cover over K is going to be the two-fold cover over a knot J. Okay. But now the question that I actually have for the audience is, do I get, if I assume that this three manifold is an integer homology three sphere, does that imply that the linking number, this linking number, and the degree of the cover are relatively prime? So I think that, you know, Chuck has done some work on this, on algebraic invariance of periodic knots, and I think that a lot of people know this, and I haven't been able to find a counterexample, but I also don't know a proof. So if somebody wants to jump in, I would be happy, or if they want to email me later on. Okay, so what's the proof of the lemma? This is actually very simple. It's the fact that, you know, like the manifold that I started with, I have a two-component knot in S3, and then I have this quotient map that gives me, again, a two-component link in S3. But what I am doing here is I am realizing S3 as the two-fold cover over what I called AQ. And so this is a two-fold cover. And then I'm taking a d-fold cover, the d-fold cover, over K. Well, it turns out that instead of taking it over in steps, I could have just done immediately the d-fold cover and the two-fold cover over this two-component link. And I get the same manifold, which then tells me that I could have started in the opposite way. I can take first the d-fold cover over the quotient of my knot K. Then I look at the lift of this knot AQ, and now I take the two-fold cover over this d-fold cover of my knot AQ. And now, okay, so I lied a little bit here. This was imprecise because this sort of implies that, actually, I said this is a knot in S3. That's not true in general. If I assume in my two periodicity definition, if I assume that the quotient knot KQ is an unknot, which it is in this case, then that's true. But in general, what I am going to get is a three manifold and a knot, right? This is this Y, and this is my J. And because what I care about in general is this idea of as U2 representations of integer homology spheres, what I really want to say is that, you know, if I have that this fold cover is an integer homology three sphere, then I also have that this d-fold cover over the quotient knot is an integer homology three sphere. And so I'm still talking about two-fold covers over integer homology spheres, which is important. Again, in terms of representations, we have this theorem, which is that if I have, again, an integer homology three sphere, I have a non-trivial knot, then the two-fold cover admits an irreducible SU2 representation. And again, the proof is by cases. So in the first case is, well, the simplest case is if this manifold Y already admits an SU2 representation, we are done. And this is because we always have a surjection of this form. And in fact, there's nothing special here as a comment. There's nothing special here about these two. Any integer over there. So, like that case, we just sort of get it for free. And so the interesting ones are when the case where Y is called so-called SU2 cyclic, which is the same thing as saying it does not admit any SU2 representation. So, of course, so maybe I should have said it, the conjecture, this problem that I am working with, the conjecture is that if I have an integer homology 3-sphere and it's not S3, then there is an SU2 representation that is irreducible, right? So I mean, here for case 2, I am assuming that I'm working with something that is conjectural. Well, it's either only, if we believe the conjecture, then I'm only saying Y is S3. But because we haven't proven the conjecture, then I have to consider this case. This is something that has always seemed very weird to me, is that we're trying to prove something, but then in the proof, we have to assume that something that contradicts the conjecture exists. Anyway, so, but in the 8 where Y is SU2 cyclic, if I'm talking about S3, then the result follows from work of Kronheimer and Moroka, and then but explicitly stated by Cornwell, Lenny, and Steven Sivek. That's the one that I mentioned when I showed the square, not the square, the chart. Sorry, the name for chart and square is the same in Spanish. My apologies. And in the case where this is not 0, this is work of Baldwin, Sivek. Actually, I should do alphabetical order. Lee, Sivek, yeah. Okay, but like notice that in the lemma or in the proof of the lemma, basically, the only thing that I am saying is that I have this equality, and that's, so I just have this commutativity of these diagrams, right? Like this is in the end all I am saying. And so in fact, a little bit more is true in terms of existence of SU2 representations, which is, if you notice, I'm already saying that if I have a 2-component knot in which one of the degrees is 2, then I'm going to have an SU2 representation. And so in general, if I have a link with non-trip, doesn't matter, such that the linking numbers, let me say it this way, every component lifts to a knot in any, say, the D sub j cover of the J component, then and this is very disorganized. I should have said, if I want to look at the DI cover of each one of the components, or I want to consider my link L, and I am going to consider only the branch cover that is related to taking any curve in the complement of the link and then just looking at the linking number mod di between this curve and the ith component. That's what I mean by this linking, by this branch cover. Then if I have this condition, and I have that one of the DIs then this cover also has SU2 representations. Right. So even though this is not the way we presented it in the paper, the proof can be adjusted to show this more generally. And I just wanted to mention that this condition that I wrote here, every component Li lifts to a knot in this branch cover of any other knot, is the reason why I need to include that this linking number over here is relatively prime to D. That's the same thing, you know, for a two-component link, saying that the linking number is relatively prime to the degree of the cover is equivalent saying that AQ is going to lift to a knot in the default cover of KQ. That's all that I'm saying. And that is something that I need if I want to invoke the theorems of Kronheimer-Moroka and Baldwin-Lee, Civic, and yeah, because those talk about two-fold covers branch over knots, not over links. We run into more problems if we start considering branch covers over links that are not of this form, right? Like this is I'm basically just taking the branch cover of each one of the components and somehow putting them together. I'm looking at the ciphered surface of each one of the components. I'm not looking at ciphered surfaces whose boundary has more than one component, is what I'm trying to say. Okay, and so what's an example of this knot, of these types of manifolds? So if I look at the two-bridge knot, any two-bridge knot is going to be two periodic, and this is an example. And this is the way in which we see that all of them are two periodic. So what you have to do is you start with a rational number, and I forgot which one this one is. Let me cheat and look in my notes. This is the two-bridge knot 23/16. And what you do is you have to look at a continued fraction expansion that only has even numbers. So it's not the usual one. And that one, then you can just always draw this ciphered surface. You see that here, this -2 is this -2. Then here I have a 2, then a 4 that becomes 2 and 2, right? Like that's why I need even, because I push the strands in each direction. And then I have, so these two are the same. So this is like knot K, and this is the knot J that I am going to get whose, in this case, I need the fivefold cover. That's what I do. Because for two bridge knots, the quotient link, the quotient knot is going to be unknotted, then I still have branch covers over S3. And in general, you know, like if you have a two periodic knot, then you're going to be able to realize it in terms of a tangle like this. And so if you have a default cover, to get J, what you take is you take this tau, this tangle, but you take it D times. And then close it up. And that's how you get the J in general. Okay, so that's that. And so, you know, like it's a simple condition on knots, simple enough, or at least a condition that can be checked in many ways algebraically. And yet we get the existence of SU2 representations. Okay, and now, well, are there any questions, or does anybody have an answer for my question of whether I do actually need to include this condition in green if I assume that my default branch cover is an integer homology sphere? Chuck, do you have an answer? Okay. Good. Now, the second part is the part that does actually involve a little bit more of gauge theory. I mean, here in this part, we rely on gauge theory, but we rely on results of other people. We don't develop anything new. There's just an application of results that have been known for a while. The second part, the moral is that if we look, we want to find non-trivial elements in some instanton homology groups. Of the cover. And the theorem, which is more general, applies more general than just for covers, is the following. I start with Y an integer homology 3-sphere, and I say that suppose that Y is going to be some form of surgery on S3 along an n-component link. So by this, I mean Fi surgery on Li, right? It just that's my notation. And if A is the linking matrix of this link, and I know that for the assumption is that if there exists an I for which the framing is greater than or equal to the new sharp invariant of Li, or maybe I can get away with one less, or maybe I need to do one more. I will tell you in a minute what this invariant is, but there is a number that I can associate to each one of knots in S3. And if I have that the framing satisfies these bounds and A is negative definite, then there exist irreducible SU2 representations. Okay, just before let me tell you what this number is, or some properties of nu. So to define nu sharp for knots, we have to consider, we have to look at the trace, any end trace cobordism, which is the one that we get by attaching a 2 handle to the cylinder on S3 in such a way that the core of the 2 handle is attached to K with framing N, right? And so this is a cobordism from the 3 sphere to precisely N surgery on the knot K. And so we can look then at the map that this trace, this cobordism induces on I sharp. And then I'm going to assign this number. I'm going to define this number for my knot K. I'm going to say, take the minimum over all of the natural numbers such that this map, the N trace map, is 0 for every N that is bigger than or equal to N. And then nu sharp is defined as the difference between this minimum number minus the one that we get by looking at the mirror of the knot. That's the definition. This is a definition. This is not ours. This is a definition of Baldwin and Sivek. And so what I want to point out is that our theorem, the way I'm stating the theorem, as it is going to happen, like these bounds have to do with the triviality or non-triviality, depending on how you think about it, of these trace maps. Okay, but so let me just give you a few properties of this invariant. So it is a concordance invariant. So in particular, if you look at the invariant of the mirror of the knot, then you have to take the negative. We also have that in absolute value is less than or equal than the maximum between the 4-ball genus, smooth 4-ball genus, to G4, or the Euler characteristic minus the Euler characteristic, and 0 of embedded surfaces in the 4-ball. And if K is an instanton L space knot, which includes positive torus knots, then we have that, in fact, this invariant is completely determined by the 3 genus of the knot, not even the 4-ball genus, but just the 3 genus. And finally, in terms of a little bit of contact geometry, what we have is that the maximum self-linking number of a knot is less than or equal than nu sharp of K. So, like if you know nothing about I sharp or nu sharp, then maybe you want to think about bounds in terms of the self-linking number, right? If you're more comfortable with that. And so in terms of what types of knots, then, like what are the cases in which I have to consider these conditions? Allow me to be vague just for the sake of presentation. And let's say that because nu sharp is going to be a concordance invariant, then this last case is going to be more or less the cases where the knot that I'm looking at is of finite order in concordance. But I think, and this is me, and if you know better than me, maybe correct me, but I think that if a knot is rationally sliced, then it's also going to be on this class that is called, it's really called W-shaped in Baldwin and Sivek. And this implies, in particular, in these two last cases, imply that nu sharp is 0. Then on the other side of the spectrum, this first case is related or is similar to the case where we have instanton L space knots. Includes that class, maybe it's a little bigger. And then the second one, it's not going to be anything that is finite order in concordance, so it's still going to be non-trivial, but what's going to happen is that for both the knot and its mirror, this minimum number is going to be exactly 0. And so those are, like examples of these are going to be twist knots of the form, an even number of crossings, and then a positive clasp. So all of these twist knots are going to be included in these ones, except for, let's say, even greater than 6, so as to exclude the figure 8 knot and stevedore's knot. Okay. So this is our theorem. Like I said, it applies more generally. It applies whenever you have a special type of surgery presentation for your integer homology sphere. But so what are examples? How can we produce examples of these, right? And so let me show you one first example. So if we look at the knot 10-132, so this is my knot 10-132. And then what happens is that the threefold cover of this knot is an integer homology sphere, but the signature doesn't tell me. The 3 signature doesn't tell me whether there is an SU2 representation for this cover or not, and this knot is not quasi-positive. So like all of the ways of finding an SU2 representation for these branch covers that I mentioned at the beginning do not work for this particular knot. But we do know that this knot is a knotting number 1. That's the unknotting curve. This is, what I get when I do the isotopy that actually unknots K, but I keep track of the unknotting curve gamma. So this is gamma here. This is the unknotting curve gamma. And then what I am relying on here is the fact that I get that the threefold cover I can get by just looking at the lift of each one of gamma to the threefold cover. And so I get that this homology sphere is going to be the surgery along the lift of the unknotting curve gamma to sigma 3 of the unknot, which is just S3, right? Like that's the key here. If I cannot knot it, then maybe let me look at it as an unknot. Take the threefold cover over that unknot. That's just S3. As long as I keep track of what happens with this unknotting curve, then I'm just going to get the surgery representation. But the problem here is that the linking matrix is just the 3×3 negative identity, or -1 times the 3×3 identity. And so, like you can get a surgery representation of S3 with this linking matrix. So this cannot work, right? Like my theorem cannot work for this surgery representation. But what happens is that each one of these components, the lift of gamma to the threefold cover of K is a 3-component link. It's symmetric. So all of the components have the same knot type, and all of them are unknotted. And so if I blow down one of the components, then I get this surgery description in terms of 2 knots. And because I started with surgery coefficient -1, and then I did a blowdown along linking number 0, right? That's what I'm saying. Then this is I still have framing number -1. And then so then the next thing that I need to figure out is what's the knot type of each one of the components. And then, but then you do the work, and then you're lucky, you do the isotopy, right? And the isotopy, if you ignore one of the curves, then this is going to be the knot, each component is a 5-2, and then you look at John and Stephen's paper and then realize that the new invariant of 5-2 is -1. Oh, so then that means that we're in this case. And so as long as I have that my framing is greater than or equal to I sharp, to nu sharp, then I'm good to go. So then our theorem then gives us, so this is equal to the framing. And then we're good to go. Okay. I don't have a lot of time, and so let me show you one more example of how to get constructing covers that have these a knot whose fivefold cover admits an SU2 representation. And so if you notice, what I did in the previous example was I started with an unknotting sequence for my knot 10, 132. And then in the unknotting sequence, or usually what we require is the linking number between gamma and the knot to be 0. But that's because if I want to construct all of the covers, then that works. That gamma is going to lift to a link in any cover over the knot. But if I have a specific cover in mind, then all I care about is being 0 mod that particular degree. So if I want to construct a fivefold cover that is an integer homology sphere and that admits an SU2 representation, I can construct my knot in this way. So this is my knot. This braided curve is believe it or not, is actually an unknot. This is the closure of this braid is an unknot. To see it, like you do Reidemeister 1 on all of these ones to get rid of that crossing. You do another Reidemeister 1 over here, and then here I have 4 crossings in one direction, 5 crossings in the other direction. So 4 of them cancel out, and then the other one is another Reidemeister 1. And so there's a more general way of constructing tangles that are going to satisfy this condition. But the key here, okay, so then if you want to know the knot is this one, right? So according to Snappy, well, is this knot, if you allow me to leave it in terms of some extra surgeries, but it's a knot, I think, what was it, is a 30 braid knot, and I think the number of crossings is 180 something. So, like it's not, unfortunately, it's not a knot that we can find in knot info. So these knots are very complicated. However, we are constructing it so that the linking matrix of this of the fivefold cover, so the linking matrix of the lift of this to the fivefold cover over the unknot is negative definite, and the knot type each component is T25, which has nu invariant. What's the 3 genus for? I forgot. I think this is 3. And these ones, the linking matrix of these types of surgery presentations that are obtained in this way, they're very simple. They're completely determined by what happens in the first row, and then you just cyclically rotate. And so the first row of this one, this is what's called a circulant matrix. And this has first row 3, 2, 3, -2, 1, 1, -2. And so you see that the framing is exactly the nu sharp value of the knot type. And so that's how we, like you can just construct the examples very easily. So I don't know, are there any questions about this example? Okay. So now let me tell you maybe very, very briefly how we prove this theorem. The key here is that I am allowing myself to use an invariant that comes from a homology theory that allows for the presence of rational homology spheres, not just integer homology spheres. But what we're saying, okay, so the theorem, part of the theorem is that we're saying these conditions so this is our lemma, is that the map induced by the trace on a knot K, which in this case, I guess I'm calling Li, is 0 if and only if, where this is right. So we're just saying this is exactly when this happens. And then the second lemma is that, well, now let me have my surgery description the way I had it before. I have my integer homology sphere defined in this way. Let me say that W is the four manifold that I get by handle attachment. In such a way that, you know, I realized Y as the boundary of this W. And so if one of the LIs satisfies the bounds, say lemma 1 and lemma 2. Then what I have is that the map, the entire map that I get from this cobordism is 0. And then the actual way in which this becomes important is because if we consider the map that you get now, no longer on just I sharp or I frame, but this is for any homology sphere and a knot K, we have the, and I forget the precise order of all of the adjectives, but if I have singular equivariant, homology, I still have the induced maps on the cobordism, and so what the lemma sort of like the TQFT properties. And I am going to only restrict my attention to the case when I have my three manifold and a non-knot. So basically, you know, if I'm just looking at, I take Y and look at the connected sum with an unknot in S3. And then I just, oh, sorry, I should have said. And so now this, I'm going to look at this space for both my three homology sphere Y and for S3. I look at the cobordism that I get by just taking the trivial concordance between these two unknowns. And what we're saying is that this is 0 if and only if the induced cobordism map on a frame instant on homology is 0. And it turns out, I mean, of course, I'm not explaining this very well, but the idea is then from this, one can show that, or rather, the map induced by this pair in the complex of these singular equivariant homology groups is non-trivial, but it is trivial in homology. And because, so what happens is that this gives me, this gives the existence of, and that's the key of using this equivariant stuff, of an element of the chain group, of the regular chain group of maybe Floer's original definition, such that it starts, such that the modulus space starting at alpha and going to theta is non-trivial. And so, so then alpha, well, alpha exists, and so alpha gives an SU2 representation, is the idea. I think that proof was very rushed. My apologies, but that is basically the idea. The idea, to recap, all of these conditions are so that I can say, actually, if you look closely at the complex generated by irreducible representations that maybe have a certain framing condition around a knot, but in this case is the trivial knot, then you look carefully at that complex, and that complex is going to have more than just the trivial connection. That's basically what all of these conditions are telling me. Okay, that's it. Thank you.
So, are there any questions?
Juanita, the dot not 10132,
Yes?
do you know what its signature function is?
I have it in my notes. I mean, we can check not info, right?
It says that usual signature is 0, but no signature function there somehow.
I think so. 10.
132.
Looks like you clicked on it.
Yes, so I see. So there is a
somehow
jump.
Right. So there are, the signature function is going to give me, some, for sure, some of these. If you have a degree whose roots of unity fall into this area, then you immediately have SU2 representations. But the 3 roots of unity fall outside of that area.
Oh, I see.
That's the
Okay.
problem. Yeah, it's not 0, but still, you know, like it's 0 on all of the roots of unity for that particular degree. Yeah.
So if you take higher order covering, branched cover, then it will be detected,
Yeah.
but not by 3. Okay, got it.
As
Thank you.
long as it's an integer homology sphere, you know, like
Yes, of course.
This is very cool. I like all of the topological arguments being put in.
Thank you. Yeah. I do,
So,
you know, like
hey,
then
can I just ask, because my picture cut out for quite a while. So what was the role of the linking matrix being negative definite? And also does it matter if it's, like, do you get something stronger if it's like not diagonalizable, or does the actual matrix itself play any, could you get some, like a little extra juice out of that if it was
no, well, you know, like I don't so non-diagonal being diagonalizable and non-diagonalizable in the end doesn't matter, right? Like this example is a very diagonal matrix, right? Like in the end is you get the 2 by 2 minus the identity. So it applies even when you don't have any diagonalization, even when the matrix is diagonal.
No, I was kind of suggesting that the opposite might, like, if you think about, if without the knots, if you have a cobordism with, say from the 3 sphere to some homology sphere, and it's non-diagonalizable, negative definite but non-diagonalizable, then that's kind of some version of Donaldson's theorem, as expressed by Freshoff invariance and so on. So I just was wondering whether the sort of interaction with these new invariants and so on was of that sort. And so if you had a more unusual sort of linking matrix, whether you could get a stronger result. That's really the point I was driving at.